Hey Panthers, it's Mrs. Sherburne and I'm back in my kitchen. And again, instead of some cooking, we're gonna do some chemistry. And remember, we're talking about different types of reactions. And this is video 3 of a 5-part series. In the first 2 videos, if you didn't take a look at those, they focused on the combination and decomposition reaction. For this demonstration that we're gonna do today, and again, this is a demonstration that you would have seen live in class or done with a lab partner. We're gonna, we've got 3 left, so this demonstration is gonna focus on one of these 3. For all the demonstrations that we're doing, we're gonna be able to balance the chemical equation is our first goal, identify which of the 5 types it is, and be able to draw a picture or a particle model of that chemical reaction. So the reaction that we're gonna focus on today is known as the thermite reaction. And I need my trusted assistant to help me with this one. So you're gonna hold up this piece of paper, and what I have here are iron spheres that were quite rusty. They're covered with iron oxide, that's the chemical name for rust, and then I covered them with aluminum foil. So I'm gonna force the aluminum and the rust to react. And I'm gonna do that with force. So Andrew's gonna hold just this piece of paper and I'm gonna hit the spheres together from either side of the paper. You ready? Now I want you to smell it.
Smells burnt and smoky.
Okay, so thank you. I'm gonna set it right there. So the other cool thing that if you were in class with me right now, I would let you try this next reaction. If I take some force, but instead of going at like that, I'm gonna have like this swiping motion, okay? And so a tremendous amount of energy is released when aluminum and iron oxide react. Okay? That's the thermite reaction. If I were to take powdered rust, powdered iron oxide, and powdered aluminum, the reaction is so strong that it actually produces molten iron. In fact, the Allies and the Germans in World War II would make bombs out of powdered aluminum and powdered rust that were essentially impossible to put out. So let's talk about the chemistry and what's going on at the particle level. So I have iron oxide, which is my rust, reacts with aluminum metal. I forced that reaction to produce aluminum oxide and iron metal. If I had the powdered forms, I would actually have molten or liquid iron because it burns so hot. This is just a little bit safer of a version. Okay, so I drew a picture, and I know some of you are asking or thinking, well, how did you know that this was going to be the formula? So if you go back to your gold sheet and talking about the charges that atoms like to make, we already know that oxygen has 2 outside electrons, and so when it loses those 2 electrons, it forms a 2 negative charge. Iron, sorry, I think I said loses 2 electrons. It gains 2 electrons and becomes 2 negative. Whereas the iron loses 3 electrons, and so he becomes a positive 3. Combining these 2, kind of a common multiple type thing, if I were to take 3 and 2, the common multiple is 6. So to write that back, the formula for iron 3 oxide, I'm gonna need 2 of the irons. 2 times 3 positive would give me 6 positive, and I'm gonna need 3 of the oxygens. 3 times 2 negative would get me 6 negative. So I have 6 positive, I have 6 negative. The formula that I write ends up being neutral. 6 positive balances the 6 negative. So I drew my picture here. I have my 2 irons, I have my 3 oxygens. Aluminum is just Al, solid. So I just have 1 aluminum atom. I'm trying to balance the reactants with the products. So I'm going to give you just a second to take a look at this, or maybe pause the video. What am I going to need to do to balance. Both sides have the same number of aluminums, irons, and oxygens on both sides. Go ahead and pause the video and think about that for a second. Okay, if you said to yourself, Mrs. Sherburne, the reaction already has the same amount on both sides. It actually doesn't. If you were to take, I have one Fe here, but over there I have two. On this side I have two aluminums and only have one. So if I have two irons on that side, I'm gonna need another one over here. Iron's not diatomic, so don't draw it touching together. It's a separate Fe. So now my Fe's are balanced. My O's are good, 3 and 3. And if I have two aluminums, then I'm gonna need another aluminum over here. Okay? So now I just need my coefficients in front of my equation. How many molecules or formula units of iron 3 oxide are there? There's only one. Do I have to write the one in front? I don't. I can leave it off of there. How many separate aluminums did I draw? 2. There's one aluminum oxide, so you can put a 1 there if you want, but you don't have to. And then the iron has 2 separate ones here. All right, so we've got our picture drawn, we balanced our equation. The third thing we need to do is identify what reaction type this is. And as I flip this over and I look at the 5 different types, I want you to think about here that iron and oxygen are together. They're bonded together. Aluminum's all alone. After the reaction, you have aluminum bonded with oxygen, and now iron's all alone. It's kind of like you have this couple here, and iron is dating oxygen, but they break up. And then aluminum, the oxygen is way more interested in hooking up with the aluminum, so they combine, and then the Fe, poor iron, gets kicked to the curb. Okay, with that in mind, we have 3 choices left. Which of those 3 do you think the thermite reaction is? If you said single replacement, you are right. Thanks for watching, Panthers. Stay tuned for video 4.